All right. So now let's look at the quantum hypothesis. Okay, so again, we're not going to be going into details. Let's just talk briefly about the history. There was this scientist called Max Planck, a German physicist. So what he did is that he hypothesized that warm bodies emit radiant energy in discrete bundles called quanta. So energy in each energy bundle is proportional to the frequency of the radiation. So Einstein and other scientists stated that light itself is quantized. A beam of light is not a continuous stream of energy but consists of countless small discrete quanta of energy. Each quantum is called a photon. Okay? Is light a wave or a stream of particle? That's now where the confusion comes in. Do you consider light a wave or do you consider it matter? Okay? Do you consider it particles? Light can be described by both models. It can exhibit properties of both waves or a particle, depending on the experiment. So, the amount of energy in a photon is directly proportional to the frequency of light. So, energy is directly proportional to small f. Small f stands for frequency. So, let's check this out. In the relationship E, which is energy directly proportional to frequency, the symbol F stands for the frequency of the emitted light, while E stands for what? It stands for the energy of the photon. Okay, so again, we say that light is emitted in discrete packets that we call quanta. Okay, and so the energy emitted by a quanta is called a photon. So which of these has the greatest energy per photon? Which of these has the greatest energy? Blue light. So blue light has the greatest energy. Why? Because it has the highest frequency. Okay. Which of these photons has the smallest energy? Infrared has the smallest energy. Now, using the quantum hypothesis, you have another scientist, a Danish physicist called Niels Bohr. He explained that the formation of atomic spectra was as follows. The potential energy of an electron depends on its distance from the nucleus. When an atom absorbs a photon of light, it absorbs energy. Then a low potential energy electron is boosted to become a high potential energy electron. So remember atomic excitation that we saw in the previous video? So atomic excitation happens when an atom is heated. The electron in an atom is going to absorb the heat and is going to be excited and promoted to a higher potential energy position. So using quantum hypothesis, when an electron in any energy level drops closer to the nucleus, it emits a photon of light. Bohr reasoned that there must be a number of distinct energy levels within the atom. Each energy level has a principal quantum number of n, where n is always an integer. The lowest energy is n is equal to 1 and is closest to the nucleus. Again, don't worry, I will show you all of this in a diagram so you understand what principal quantum number means and what energy level means. Electrons release energy in discrete amount that form discrete lines in the atomic spectrum. Okay, so which of the following is a quantum number? So again, if you go back, we said quantum numbers are always integers. What that means is that they have to be whole number. You cannot have fractions, you cannot have fraction. It's always a whole number. So that's why a quantum number here can only be 2, because 2 is the only integer. So Bohr model explains why atoms don't collapse. Electrons can lose only a specific amount of energy equivalent to transitions between levels. An atom reaches the lowest energy level called the ground state, where the electrons can't lose more energy and move closer to the nucleus. So Bohr, which is that same Danish scientist, he brought up what we call the planetary model. And so photons are emitted by atoms as electrons move around higher energy outer levels or energy levels. The energy of an emitted photon is equal to the difference in energy levels between the two levels. Because an electron is restricted to discrete levels, only light of distinct frequency are emitted. Okay, so now look at an electron wave's nature. Okay, electron waves. An electron's wave nature explains why electrons in an atom are restricted to particular energy levels. Permitted energy level are a natural consequence of standing electron waves closing in on themselves. So the orbit for n is equal to 1 consists of a single wavelength, right? While n is equal to 2 consists of two wavelengths, and so on. So now let's go back to the atom now, begin to look at diagrams. For a fixed circumference, only an integral number of standing waves can occur, and likewise in the path of electrons about the nucleus. So you can look at this diagram right here. So these waves, this wavelength constitute what you have around the nucleus of an atom. So somewhere in the center here you have the nucleus, and then these waves represent actually where you can find electrons. So if you cut the atom, suppose you're cutting the atom. So the atom is obviously spherical in nature. Okay, so if you look at the center here, you have the nucleus. That's where the center is. And now surrounding the nucleus, you have what we call what? Orbit. So this is what we call energy levels. Okay. That is where electrons are. So when we're talking about atomic excitation, what we mean is that you can have an electron where you see these two on this first orbit. You can have an electron here. When the atom is heated, that electron is going to absorb heat and is going to be promoted to the higher energy level. Okay, that's called atomic excitation. When electrons are promoted to higher energy levels, again, these circles are called energy levels. They are called energy levels, they are called shells. And n is equal to 1, or all these shells, they have numbers, and they are assigned numbers that we call principal quantum numbers. So n is equal to 1 is for the first shell. So principal quantum number 1 is represented using n. Okay. All right. Another one is you have the shell model showing the first three periods of the periodic table. Okay. So for each atom, you have shells that represent where these electrons are found. Again, I said we're going to talk about shells. So there we go. So the first element has one electron because it is position number 1. And so remember, number of protons and electrons are always equal. So if hydrogen is position number 1, it means that it has only one electron. If lithium is position number 3, it means it has 3 electrons, because position number 3 means it has 3 protons and therefore 3 electrons. And so how are these electrons arranged? They are arranged around the atom on the shells. And so each shell is just like a room with a maximum capacity. The first shell can only take 2 electrons. That's why you see for all of this arrangement, you will see only 2 electrons on the first shell. You will see only 8 electrons on the second shell, because these shells have a maximum capacity they can take. But the whole idea here is you need to understand that an atom is made up of a nucleus, and surrounding the nucleus, you have shells. And on these shells, that is where the electrons reside. Okay? All right. So that is that for this video, and hope you understood the main takeaways.